Hello dear students, welcome to our fourth video, and I hope you watched the previous three videos and you are informed what will be done today. Today we are going to discuss on resistors combinations. If the resistors are connected in series or parallel combination, then what will be the total resistance, along with the formula and calculations with examples we will try to understand. Besides, we will also go for a new quantity, that is resistivity. You know about resistance. There is another quantity which is a little bit different than resistance. That one we are going to understand, and finally we will know a new instrument or component, that is LDR. LDR means light dependent resistor. So we are going for discussing the combined resistance of resistors connected in series first. You know what is called series connection. If we add more than one resistor, one after another, that is called series connection of resistors. I am showing you in the diagram. Look, here there are three resistors here, R1, R2 and R3. They are connected in series, one after another, and to get the total resistance of these three resistors connected in series, there is one formula. Here I wrote RS. It's written there, you look. RS equals R1 plus R2 plus R3. If we have more resistors, like if you have 4, 5 or more than that, then we will add the similar way, R1 plus R2 plus R3 plus R4. This way we will add them. And here I gave also the numerical values of the resistors. For R1 it is 2 ohms, R2 it is 4 ohms, and R3 8 ohms. If they are connected in series, then we will use this formula, RS equals 2 plus 4 plus 8. So we are getting combinedly here 14 ohms. That means if the resistors are connected in series, then the combined resistance is more than any one of them. You will see our combined resistance or total resistance is 14 ohm, and it is bigger than 2, 4 or 8 ohms. That means if we connect the resistors in series, then the resistance of the whole circuit increases, then current flow will be less. Now if the resistors are connected in parallel, you know that if they are connected across each other, I am showing you the diagram here. See the diagram of parallel connections. Here the three resistors, 2 ohm, 4 ohm and 8 ohm resistors, they are connected across each other, and they see in the left side and right side, they are meeting at one points. That's why this is called parallel combinations. And if it is in parallel combination, then we are using another formula, that is you see the formula is 1 by Rp. Rp stands for total resistance in parallel combination. So 1 by Rp equals 1 by R1 plus 1 by R2 plus 1 by R3. If the number of resistors are more, then we will write this way, plus 1 by R4 plus 1 by R5, this way, and so on. Here we got numerical values of the resistors, so we can put them in the formula 1 by 2 plus 1 by 4 plus 1 by 8. If you calculate them, then you will get 0.875. And look at the last line. We got here RP. We had 1 by RP, but we are inversing it or reversing it. We are getting here RP because our target is to get RP, not 1 by RP. So we are inversing it at the last step. So RP is equal to 1.14 ohm. If you get 1 by 0.875 in your calculator, then you will get 1.143. We wrote here in 3 significant figures. That's why we wrote here 1.14 ohms. So is the way to get the resistance, combined resistance of series and parallel combinations. I think you can do them. In our CIE past paper questions, we don't get more than 3 resistors connected in parallel or series. Sometimes we get series and parallel, both are present in the same circuit, so that time we have to do them separately for series and parallel. And finally we will check the connection, which formula will be applicable. If it is in series connection, then we will use the formula of series. If they are in parallel connection, we will use the formula of parallel. We will do it in the worksheet. I already uploaded the worksheet in the Google Classroom. You can check it over there. If you don't understand, or if you don't get the question how to do it, then please ask me in the comment link. I will answer your questions. Now we are going for the next item, that is resistivity. Resistivity, I told you, it's a little bit different than resistance. Before going to the difference, we will try to understand the basic from where the resistivity came. You know that resistance is the quantity which prevents the electrons flow in a conductor. So think of if the wire or the conductor is longer, like if you are taking a shorter wire and you are taking a longer wire, so which wire has more resistance? Let's relate it with our practical life. You think of that you are walking through a path, and if the path is, or the road is long away, then it will make you more tired. Then you cannot go there fast. So if the electrons also get a longer wire, they get tired. So if they get tired, it becomes or it creates more resistance. So we can say in the longer wire there is more resistance. In other way round, we can say resistance is directly proportional to the length of the wire or length of the conductor. Again, think of a street or road. You are driving a car. If the road is narrow, then it's very difficult for you to drive the car. You cannot go so fast, you have to go slowly. But if the road or street is wide, then you can go there fast and you can go there smoothly. Similar to the electrons, if the wire or the conductor, it has more thickness or more diameter or more radius or more cross-sectional area, then the electrons can flow easily. That means the resistance becomes less. So this one, in numerically we can say resistance is inversely proportional to the cross-sectional area. Again, I am repeating, resistance is inversely proportional to the cross-sectional area. That means if the cross-sectional area increases, then resistance decreases. If the diameter increases, then resistance decreases. If the radius increases, if the radius increases, then the resistance decreases. Or if the thickness of the wire increases, then the resistance decreases. You can relate with each other. Now, if we see it here numerically, I think it will be more understandable for you. Look, I wrote here R is directly proportional to the length. So, length I represent with L. R is proportional to L. Here L is the length of the conductor. Then we have cross-sectional area A. R is inversely proportional to cross-sectional area. That means R proportional to 1 by A. Here I gave a little bit description. A is the cross-sectional area of the wire or conductor. We know A equals pi r square. You know R is the radius of the wire. So A depends on the radius or diameter of the wire. Already I told you about the relationship. Now, if we combine both length and cross-sectional area, then we get here R is proportional to L by A. So, according to the mathematical rules or numerical formulas rule, we have here one proportionality constant. You see here I wrote here R equals rho L by A. Here rho is the Greek letter and it is the proportionality constant, and this proportionality constant we represent as resistivity of the conductor. Resistivity of the conductor. In bracket I wrote of the element. Actually resistivity directly involved with an element like copper, iron, silver or any other conductor. They have whatever the cross-sectional area or whatever the length is, always for a same element the resistivity is same. And if you rearrange the formula, it comes resistivity, that is rho equals R A by L. Rho equals R A by L. Now, as you got a new quantity, we will go for its SI unit, and the SI unit of resistivity is ohm meter. You see, SI unit of resistivity here is written ohm meter. And how this unit came in class also I told you, you don't worry to remember or memorize these units. If you know the basic units, then it will come automatically. I showed you here, I wrote the formula. Look, rho equals R A by L. You know that SI unit of R, resistance, is ohm. Cross-sectional area means pi r square, so its SI unit will be meter square. Then length, the unit you know, that is meter. If you make it simpler, then it comes ohm meter. Meter square by meter, then 1 meter goes. So we have here ohm meter. Now you might be sometimes you will be messed up with resistance and resistivity. That's why I gave here the difference. Look, you will understand it now. What is the main difference? Look, from the previous discussion you already understood that resistance depends on the length and cross-sectional area of the conductor, but resistivity is same for the element. For example, if it is copper, then resistivity is constant whatever the length or cross-sectional area is. I also gave sometimes one example for resistivity. It's quite similar to density. You know, if I take one measuring cylinder of 100 centimeter cube, and we measure the density of water. You know, the density can be measured using the formula mass per volume. So if you take the mass of the water and volume of the water, if you put in the formula, you will get the density. It will come 1 gram per centimeter cube. Normally, what is the value of density of water? And if you take a bigger one, like you are taking 200 or 500 centimeter cube measuring cylinder, that time also you measure the mass, measure the volume, then you will get the same density, that is 1 gram per centimeter cube. So for a particular liquid or particular element, the density is same. You can change the volume, you can take the different mass, but the density will be same. Similar to resistivity, you can take more longer wire or you can take more wider wire, there is more cross-sectional area. Whatever you are taking, or you are taking a shorter wire, you are taking thinner wire, that's not affecting the resistivity. Resistivity for the same element, it will be the same. I think now you understood it clearly. Even after that, if you have any doubts, please let me know. We will discuss the matter again. Now the last item of this today's video, that is light dependent resistor. From the name you understand that it depends on light. The resistance of this resistor depends on light. how it depends, and that is this type of resistor we actually use in more complex circuit like street lamps or intruder alarms, burglar alarms, and many other places. Now in this topic, current, electricity and DC circuits, we do not need to know so much about LDR. We will know its more application later on. Just you know the symbol and how does it work, and the basic only. Look here, I drew here light dependent resistor symbol. It's very easy. First you have to draw one resistor, then you are showing with arrow, two arrows towards the resistor, that is showing that it is light dependent. And how it is light dependent, I wrote here, if light increases, resistance decreases. I repeat, if light increases, that means the light is falling on the resistor. If the intensity of light is more, then the resistance of the resistor or LDR decreases. So if LDR is connected to a circuit, if there is more light, then what will happen? The resistance, the total resistance of the circuit will decrease. As a result, we will get more current in the circuit, and this way we can make different types of appliances. So today we are at the end. Hope you understood all the three items. Let's recap. First we discussed about the resistors connected in series and parallel, their combined resistance, how to calculate. Later on we understood what is resistivity and the formulation of resistivity, how resistors or the resistance of a conductor depends on the length, depends on the cross-sectional area, and how it is linked with resistivity, and what is the main difference of resistance and resistivity, their SI units. Finally we understood what is light dependent resistor and how does it work in a circuit. Thank you so much for listening. Stay safe. Best of luck.